¿Estudiando juntos? ¿Saliste juntos?
Sí, no,
Lo que dijo, no te primero sobre su dinero, por lo del medio. A ver. Bueno, entonces, este ejemplo. Ah, no importa. ¿No te fue bien? Bueno, contento. Las tareas que también. Las tareas. Bueno. Sí, porque ¿sabes qué? Tengo menos peso, boludo. No es que no tengas más. No, no es de 5 días. Es con la mitad, como 40 semanas. Bueno, entonces no hago más. Bueno, un beso. Chao.
Just put not canceled, right? Not
I
canceled.
hope so. I thought I was checking my email because somebody was here and it's almost 7.
Oh, yeah.
I said, well,
What happened?
When you came in, I said, okay. Get someone else like me.
Yeah.
Are you from Korea too?
Yes, I'm from Korea.
From which city? Seoul?
So, actually, he graduated here.
Yeah, I graduated from here.
Ah.
I'm a class of 06. And I graduated 7 years ago from here to this department.
And you graduated and went to work to Korea?
No, I was working here.
Ah, here.
I worked for about 3 years, respectively.
Yes.
And then I had to go back.
Which line?
Well, I was drilling.
Drilling.
Yeah. Gulf of Mexico.
Yeah.
But I had to go back to Korea to start farming. It's mandatory for every man in South Korea.
To go back to?
To go to army. We'll start army for 2 years.
To go back there and go to army.
Yeah.
How long have you been in the army? You born in Korea?
It was okay. It was a good experience. But I feel like my way is a lot of fun.
Lived a long time. There is only small amount of shooting, except for the shooting practice. We need to make document for report.
A lot of paperwork.
Yeah.
Shooting.
Yeah, and hold on.
Consistent, their training, for some positions, their training is more rigorous. But most of them, I went to range like twice or once throughout my entire military service. So no shooting.
No shooting.
Were you located in the border with North Korea?
Yeah, I wasn't looking for it. I was in South.
So, join the army, the United States Army. The name is Katusha.
You have a joint army with the U.S.
Yeah. Well, South Korea. U.S. Army is based. Their camp is in Korea as well.
They have
Yes.
camps in Korea.
Yeah. So I was working at their camp.
They have military bases in Korea.
Right.
Korea and also Japan. There are several bases in Japan.
Yes, they have military.
Yeah,
They have in Germany.
Yeah, one in Korea. We call it the same. Yeah, military plan to protect China and Russia.
Mr. Korea.
Hello.
Are they implying I was going to be late? I'm not stupid. No, because my profile is so big that if I don't log in an hour ahead of time, I have a problem. So we think we have a solution for the remote, we think. Did I mention how much I hate this Spotify? Somebody has to open the door for the Frenchies. Paul, come see. If you ever lecture from a PDF here, there's a problem that you have to turn the preferences because it thinks it's a touch screen. You have to go to General and turn this never, okay? Otherwise, it'll drive you crazy. So, because this is a touch screen.
Okay.
So you don't want the touch screen to control the computer. So just remember, preferences, General, never. I prefer to use PDF because then it doesn't conflict with Microsoft Ink. Hey everyone, this is Paul. Say hello, Paul.
Hi.
This is Mr. Song, Mr. Gilligan, Mr. John. You're John.
Yes.
And Jorge and Smurf. He doesn't like to be called Smurf, so he doesn't like the R. Smurf. We got to talk about this. All right, John, what kind of weekend did you have?
Oh, boring.
Boring? Man, I'd like to have a boring weekend. Santiago, what kind of weekend did you have?
Many things to do.
Diamonds are made under pressure. So are other things. Where's the Frenchies tonight? They don't want to be here? Okay.
It's normal?
Hmm?
It's normal for you to this way?
No, usually everybody comes.
Usually?
Yeah. And historically, what happens is when the resident people don't come, they don't do well in the class. I'm not trying to make a prediction. I just will tell you that what happens is when they disappear, the reason the distance learning people do so well is because they block out time and they treat it like part of their job. So they do this, they have a pattern, you can see it. Well, the ones who do well, and I'm talking to all of you, so that's that. Paul behind you is going to help us this term, and we figured out a solution today to share the computer remotely, so I think we'll be able to do that. We had tried to do a remote login, but if we do remote login, it disconnects the video from the system, so that's not a good idea. So we're using a product that the department uses. It may not work to our satisfaction, so I have a plan B. Paul, do you have a Skype account? Okay, so we'll install Skype and that way we will use, if the Bridget doesn't work, we'll use Skype. We'll test that tomorrow. But what I have to do for Skype is I have to get permission to put it on this machine. So I'll do that. No, it's okay. You're French. You guys, I don't want to interrupt your, vacation with school. So what did you think of the party the other night?
Thank you.
Yeah.
That's nice.
Yeah. That's nothing. That's nothing. Just wait until you see the Sodom and Gomorrah that is the student meetings. These guys will explain it to you. And then when you go to the SPE, ATCE, just please do something constructive with that experience. There might be some people from Total there, and I'm going to spray paint some French flags on you.
I think it's very obvious that they can.
No, people think you're Texan. They were telling me. Okay, so as I mentioned, Paul is your teaching assistant in the back. He'll be here every day that I'm not, so he'll help out with that. He's also going to probably do like a recitation on the problems, and we were talking a little bit about that today. Ordinarily, I just give you the problems and say good luck, but he didn't want to do that, so we'll do that. Okay, I think everything's ready to go. Santiago was complaining that the French guys were late. No, I'm joking. So, where's the fencing? Dreyfus, yeah. So is this something he's really good at, or?
Yeah, pretty good.
Yeah. What are you good at? Tennis? You don't look it. I can introduce you to some people that will change your mind. Like 5 times your weight. Yeah. You seem overly confident. I'll take you out to the Maori rugby field. That'd be, yeah.
Oh, no, yeah.
Yeah, it'd be almost worth it to see. Yeah. Do you have a will, for what to do with your body when you die? No? Okay. All right, Santiago, you ready? Okay. So we talked about this a little bit before. All of these problems relate to the textbook, the first textbook, the edition 1, and there are probably a few copies of it around. There may be a PDF of it that you can purchase. But if you're going to do these, and obviously I've marked it, don't turn them in, then these are the problems that you should work. In the past, I assigned all these, and people were not very happy with me. So I would say if you want to know what I know, then go back and do all of these. But if you're satisfied in knowing what you know, then don't. You can think about it. Okay, so now we talk a little bit about derivatives. And I guess every time you do this, you learn something. So the important thing is everyone remembers that a derivative is a tangent. It is represented, in this case, by a reduction in the distance of evaluation. So as we reduce this distance and we take the limit as that distance approaches 0, of course, the delta becomes a tangent. What's the practical aspect of this? Do you have any concerns? No? So, as usual, I will jump out of the lecture. I know you enjoy when I do that. Am I right? French guys, do you like when I do that? You like when I jump out of the lecture? No? Go here. This one Petro thing, and we go What is 1 petro? I don't want to know what it is. I want to use it. I gotta put my glasses on. Okay, so this is Van Gogh. Did nothing come up? Man, this guy's old. I'm looking for 1983. This is why you should narrow your search. And the stupid thing clears itself every time you do it. Alright. Advanced. Okay, so this is the famous paper by Van Gogh, Roch, and Clark, and they talk about an algorithm by this French guy, and his name is Bourdet. And the Bourdet algorithm is designed to be a weighting formula, and in this case what we're going to do is going to put our make it extra fat like that. Okay, so this is the point that we're at, and we want to look this distance, and we want to estimate the derivative based on that. How would you do that? What would be the simplest thing you could think of? Well, you could use a finite difference. What happens if you use a finite difference on this, Paul? What happens when you take the derivative of a cloud, everybody? You get a bigger cloud. So if we took this data into Excel and we did a point-to-point difference, what would happen? Make a cloud, okay? So what they proposed was a weighting formula. So we're still interested in this point right here. We're interested in the derivative at that point. So we estimate a point here and here. We go look, and if it falls in this range of L, here and here, then we use those points and we make a weighting formula, and that weighting formula, we use the slope from that one and the slope from that one, and then we average them together. Now this is not relevant to finite difference calculus. This is relevant to everyday practical stuff. You're going to use this every single day in well test and production data analysis. Why use this algorithm? Okay. Polytechnique grads, you ready? You know it's coming. You know you love being called on. What nickname did we give you last? Ralph. Yeah. Okay, Ralph. Why don't we fit a curve through here, and then just differentiate the curve at our point of interest? Why not do that? That's what you would have done. Very good. So we have a vote for the polynomial. So polynomial.
It depends on the order you take in your polynomial.
Yeah, but let's say we're going to keep it easy and just make it a second order. How's that? Okay. So we have to have a window, though, that we evaluate this under. So it has to be defined. Can't you argue, am I confusing you? We have to decide how big a window we're going to use to define this. So we're going to have to be a little bit clever about that. Not too clever, but a little bit. Okay, so polynomial is one option. What's another option? John?
You could take the average of all point-to-point derivatives.
Okay, so you're saying then that you want to take this derivative, that 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 derivative.
No, we didn't do it, no.
Okay, but somehow we have to get a derivative for each one. So you're going to take the point for point.
You take the slope,
Correct?
you average the slope, but
Okay, but those go up and down. What's down, Smuff? Negative. What's up, Smuff? Positive. So the average between negative and positive might not be meaningful.
if on the whole it's going up, the average.
I see a nice experiment. Maybe you want to take a data set and demonstrate this and let them play with it. Just grab one out of the literature. I guarantee you, if you take point-to-point derivatives, it's just going to... Okay. But that is another option, point-to-point. Anybody else?
Could you explain just a little more what this ability is?
We'll come back to it. Okay? Anybody else? KJ? No habla English? What about a spline? Where we have points here and here that occur through that, points here. You know, you have knots in a spline. Something, I mean, I've exaggerated it, but something like that. Splines are combinations of polynomials. I've exaggerated it. I've made it look crazy, and it's not going to look like that.
So it's better than basic polynomial.
It's better. It's a piecewise polynomial, but it's optimized as to where you want to put the location. The knots are the fixed location, like a knot in a rope. That's what they call it. Okay, so it's a fixed location. Splines have some really elegant features, and for certain kinds of data analysis problems, they work well. If you look, one of my students that worked with Dr. Balco, they used splines for deconvolution. And that was really clever because splines, you can specify how rigid they are. You can make them stiff, and that's what we were doing here. Splines probably not an answer. Probably not what you're going to want to do. That was tried. Anything else? Any other ideas? Any crazy ideas? Jorge? You had a lot of time out on the platform to think about this.
Thinking finite differentiation. Finite differentiation.
You want to integrate it?
Not integrate, but like smooth the point.
Somehow, okay, so you want a smoothing formula.
Yes.
Is that what you were suggesting as well? Okay, but a smoothing formula, something that treats the data. The problem I have with a smoothing formula is it's probably going to be subjective. It's going to vary throughout the data set, but we can say some sort of a smoothing formula. That's been tried as well. Anything else? What about something crazy?
Just take the linear regression on the
Okay, good. So a variation of what we were talking about, what you're suggesting is a linear regression rather than a polynomial regression about this point. So it could be linear or polynomial. Okay. Any other ideas? That's actually probably the most logical thing. Okay? It's probably the best, safest idea, but it also has problems that it could walk away. It could go crazy on it, depending on how people apply it. One other suggestion, anybody? Paul, what are the rules of Laplace transforms? The Laplace transform of a function is what? What's it defined as, class? The integral from 0 to infinity of f of t e to the minus st dt. Is that right? And then what happens when we get inside the Laplace domain? That's f of s in our nature. What happens when we do that? Correct. What he's saying is once we establish this behavior, and let's say that we decided to do that, we use the point-to-point formula. Okay, Ralph? And we take that into the Laplace domain. Then how do we get out? Okay, so you want the derivative in f prime of t is simply equal to the inverse Laplace transform of f of s. Okay, like that. That's what you were thinking? Yes, the definitions are all there, but the problem is f of s. The active integration, the Laplace transform, is that a stable or an unstable act? Let's have a vote. Stable or unstable?
Stable. What do you mean by unstable?
Okay, will it go crazy? It's an integral.
Function is not regular enough.
You just have points. Unstable.
Unstable. Don't know.
I would say unstable. No. Stable. Stable.
Don't know. It's going to be stable, right? The active integrating it will be. There could be some outlier behavior that makes it go crazy. There might be something that, spike here, but you would know that, and everything would be okay. Now, what happens when you invert? All bets are off. It's going to be unstable, isn't it? If it was unstable as in the time domain, taking the derivative, I bet it's going to be unstable in the Laplace domain, inverting it.
But what do you mean by unstable?
Yeah, you're right. It's a bad word. Sorry. What do you think this is going to look like if you take it in the Laplace domain? If you take a table of data into the Laplace domain, you'll have to, the interval is 0 to infinity, so you'll have to come up with some trick about what the values are at infinity. But don't worry about that. So the question is, how would you use a piecewise continuous function and take that in the Laplace domain? It's going to be okay. But then when you come back out, it's going to be unstable.
Yeah, it's projected. It's not.
This was tried too. Who tried this? Okay. So maybe Laplace transform. Any other ideas? Any other ideas?
One thing I could think of is, we've got the shape of a polynomial, but kind of, and maybe that's what he was saying.
He was implying a piecewise linear. Splines are not piecewise polynomials necessarily. They're connected. They have certain conditions, but you're thinking about a moving polynomial, and of course that's correct. That was the first attempt, was to use a moving polynomial. Well, the first attempt was just point to point.
Right.
But the second attempt was a moving polynomial, and actually it was Paquette that was using that even as long ago or short ago as maybe 5 or 6 years when I gave them the algorithm to do this. And actually, I don't use this form of the algorithm. I use a semi-log time version of it because the data are spaced logarithmically in time. They're not spaced in a linear fashion in time. Okay, so your question, Ralph, was what does this mean? I'm not exactly sure how to explain it, but again, it's a weighting formula. Did I touch this wrong or something? We choose these limitations, and then we evaluate here, here, and here. And it's basically just a linear average of those two slopes. And that becomes your derivative.
And how do you choose that you want?
Oh, the L, that's the trick. So what we do in practice is L is a fraction of a log cycle, log base 10, okay? So if we say L is 0.1, then that's 10% of a log cycle. If we say it's 0.5, that's half a log cycle. You're probably going to stay more like 0.2, 0.25. You don't want to get too wide because then what happens? You over smooth. Now, everybody in the room, take a deep breath. This is not a petty 620 problem. This is a petty 648 problem or a petty 324 problem or a petty whatever problem. Petty 620 is looking at this problem because we may be able to develop another technique over here that improves that. That's why we're talking about it. But the actual application, what do they want? If you were writing software or if you were developing a new methodology, what would you want? What's the number one thing you want when you're writing an algorithm?
Conversion. Like you want to make sure our stability to keep it from
Consistency. Okay? Even if this is wrong, it's predictable. It will not go crazy. It will not give you totally, and you're not using these numbers to calculate something. You're using these numbers to visualize something. Okay? Everybody got that?
But
Yes.
you take the average between the front slope and the back slope on the defined window for each step.
It just moves through. There's some logic, but it moves through. Yes?
And I may have missed it, but when you're defining the points, is it kind of the average, kind of the median of those points, or?
No, it's simply looking. The algorithm goes.
And it's a real value, so a real value at that point in
Yeah.
time. Gotcha.
And then it makes the two slopes from that and then averages them with an inverse weighting formula.
Okay, and then visually.
I'm not really sure why he used an inverse weighting formula, but that is what he did, and that turns out to be the most effective. Yeah.
Is there anything to work against outliers? I know you were saying, or you.
Outliers generally, you can see them. What you really ought to ask about this device is what happens at the endpoints. Okay? And what happens at the endpoints? At the endpoints, you only get one triangle, and so it's corrupted. So as you get close to the endpoint, what you have to do is you sort of have to visualize that this piece is going to be corrupted and that piece is going to be corrupted. Now, obviously, the data set's much bigger than this, and you'll see it in the data set. It will the averaging formula will turn itself off and only one piece of it, either the forward difference or the backwards difference, will take over. And when that happens, you'll see like a disjoint. And there's nothing we can really do about it because that's the way the algorithm's set up. And you're going, well, Tom, maybe we should come up with something clever. Trust me, this is not where you want to put your effort. Where you want to put your effort is on interpreting and other things like that. And maybe there is an approach for creating some sort of a smoothing device, and we can talk about that later on. But right now, what I would say, my next question is going to make your day very unpleasant. Okay? Okay. We got the derivative. We're okay with that. We're going to use this derivative as a diagnostic. We're going to look for certain trends. Why do we want to use the derivative? So that's not the bad question. The bad question's still coming. Why do you want to use the derivative?
You mean in general or in petroleum?
It's like an accelerometer. It tells you what's happening sooner. Right? You get an indication of change. And that's important. In petroleum engineering, we're always looking for indicators. And a derivative will give you a stronger indication than the function itself. Okay? So depending on who you believe, the pressure derivative has been around either since the 1970s, the 1960s, the 1950s, the 1940s, or the 1930s. There's a whole bunch of people who claim to have invented the pressure derivative. I'm not going to argue that. There are formulations of the pressure derivative in the 1940s. There are formulations of the pressure derivative in the 1960s. Nobody was using it. Why? Because how would you have calculated the derivative in the 1940s? You would have used a triangle, and you would have marched your way through the data set, drawing graphical triangles through the data set. That's exactly what they did. There's actually a reference to the pressure derivative in the hydrology literature that's something like 1927, but don't quote me on that. Okay? Forget about the derivative. Now the bad question comes. Let's say that the derivative gives us some insight into behavior. Ready? If a little bit is good, how about a whole lot?
You're talking about a whole lot of data?
Mm-mm.
You mean you just have some data points that are correct?
Okay. Your friend Dr. Cincolay, he wrote a paper about the time you were born, and it was on superposition. And it was the first time anybody showed the second derivative in well testing. But he didn't show it applied to data. He showed it applied to the analytical functions, because of course when we have the analytical functions it's trivial to take the derivative or whatever derivatives we want. Okay, so now what about the second derivative? If the first derivative gives us a unique characterization, why not go a step further and get even more resolution? That's what I meant.
Mostly a matter of precision of the data set.
Exactly. So the derivative of a cloud is a,
Bigger cloud.
and the derivative of a bigger cloud is a, yeah. Very good. I like that, a storm. So this isn't going to work. If we were dealing with analytic functions or some sort of output from a device that had that kind of resolution, okay. By the way, how accurate are pressure gauges in the petroleum industry right now?
Very accurate. Like fractions of psi.
Okay, very good. So 1 part in 10,000? Is it 1 part in a million?
In a static condition, it's very accurate, but the well is not in static condition.
Okay. So why do you have all these little?
Because you have pressure effects, like if pressure is increasing a little, it can change.
Is it that, or is it that the gauge is moving, or is it that there's fluids moving past the gauge, shaking it a little bit, or is it temperature effects? Is it all of these?
You can tell when you get your gauge out of the well, you don't know what caused it, but the accuracy is not more than maybe 1 psi for good gauges, while
the resolution is 1,000 of the I didn't.
Sorry?
I did my last indenture.
With Schlumberger or with what? Yeah. So you're very comfortable with their ability. I mean, there's a number out there in the 7th decimal place. I'm not sure that number is meaningful. But let's say we can expect a modern gauge to be accurate within 1 part in 100,000. So probably at least 1 decimal on 10,000 psi, maybe a little more. You know. And of course they have to be calibrated and all that sort of thing. Okay. So how did we jump to this? Well, because I want you to understand that 620 is more than just equations. 620 is thinking about what we're trying to do. Now, if you were taking Dr. Moridi's class, you would be talking about finite differences today. And since I've never taken his class, I'm sure that you're all familiar with how you develop the finite difference calculus. We assume that these solutions or these functions are totally analytic and that we can represent these. So the concept of a graphical relationship of the derivative is given here. And again, our goal is simply to illustrate that the more we approach 0 with the delta x term, the more the nature of this behavior is what? This is a tangent or an analytic function or an analytic derivative. Okay, so we have the chain rule. I'll scroll up. Not so much. I don't think I can do this. Yeah, I think we're just going to have to look. Sorry about it. You'll have to look at the bottom. Okay, so we have the chain rule where we split a variable apart. In this case, we're looking at dy dx. And we're going to split dy dx. This is not fun being on the floor. dy dx. So then we have dy dx. And we have du. And how many chains can we have? French boys? As many as we want? Yes. You might have a problem dealing with gas wells where we split this out into several different variables. Why? Well, because we need to know the derivative of pressure with respect to time, but that's not what we know. So we have to break it all out. Okay, then we have the product rule. And the product rule is the derivative of uv is equal to u dv dx plus d du dx. I know this is boring, but this is important. Why? What can we use the product rule for?
Not by integration.
Well, we can take the derivative of a product, but what else can we do?
We can pull what might be very complex together to take the derivative, and it's almost kind of a piecewise.
Okay, you're on the right track. But actually, we can use the product rule to derive the integration by parts formula, and that's the direction I was thinking of going. And then you can split it into as many pieces as you want. You have the quotient rule, and then the power rule below that. I think these are pretty obvious. So, are you going to use these in this course? Yep. You will see them again. So, that is something to think about. All right, now let's talk for a little bit about integration. And of course, the fundamental theorem of calculus says that as we integrate, we'll evaluate the integral, and then it'll be the difference between the integration at 2 different points. But what I really want to talk about here is how to integrate a curve so that you'll understand what it looks like. And in this case, we have a nice functional form. We have x and f of x And we have a nice curve. And we have a point here. This is like Microsoft Excel. Point here, and a point here. Okay? So now we're going to chop this into pieces, and we're going to look at integrating it with strips. Now, what does the integration tell us? What has to happen to the width of the strip, h? As h goes to 0, what happens to this? This becomes the definition of the integral. Okay? But I want you to stare at this for a minute, and I want you to tell me, what do we do with this part? That's the error. How do we capture the error?
We don't use rectangles.
We use what?
Trapezoid.
Okay, we can use a trapezoid, which is a triangle sitting on top of the rectangle. Okay? So can we derive the trapezoidal rule graphically? Yeah, we'll do that in a minute. What's the name? If we use a trapezoid, that's a linear connection between the points. So that's saying that we're going to connect this, and that, and that, and that. That's the trapezoidal rule. What happens if we use a second order polynomial, a quadratic? So 2 points define a line here to here to here to here to here. What if we decided to use, oops, where did I move? What if we decided to use a quadratic, sorry, I used a bad color. What if we decided to use a quadratic like this? And that quadratic exactly fits these 3 points. What's that called? That's Simpson's rule. Okay. What if we decided to use an arbitrary polynomial?
What?
An arbitrary polynomial.
It depends on our regular function.
Sorry?
It depends. It's worth doing if the function you're trying to integrate is regular and irregular.
If it's continuous and if it's monotonic, then you can guarantee certain behavior as well, but some functions aren't monotonic. Okay?
No, but it has to be enough derivable.
Yes, it has to be, its derivatives, it has to be sufficiently differentiable, which we call analytic. Okay, that's great, thank you. But what would happen if you decided to start utilizing an nth order polynomial? What would that be called?
Taylor series.
Sorry?
The Taylor series?
That's actually a good guess, but I'm thinking more of how you would evaluate the function to obtain a certain accuracy using a polynomial. Do you remember what that's called? It's called quadrature. Okay. Now, we don't typically use quadrature very much in our industry because our problems are usually not well described by quadrature. Okay, we don't need quadrature for our problems. Paul, can you think of an application of quadrature that these guys might see sooner rather than later? For quadrature? No. What was the definition of the Laplace transform again? What is it?
The integral part of the derivative of things. C to d to the negative f.
kind of integral is this? Does anybody recognize it? It's a French guy. Laguerre. Okay? This is a Laguerre form. So actually we can formulate the Laplace transform in terms of Laguerre quadrature. Okay? It's not very efficient. As a sampling function, it's not very effective. But we will talk about Laguerre quadrature for the Laplace transform in this course. A little bit, not much. Santiago, why are we so in love with the Laplace transform? You know, Dr. Holditch, he used to complain for 20 years. You people live in the Laplace domain. It's not real. Why do you do it? Well, why do we do it? Why do we work on problems with the Laplace transform? Because it arises naturally in what we want to do. Okay. But getting into the Laplace domain, as we talked about before, is the easy part. It's getting out that's the hard part. Here are some rules for integration, and I think in the interest of time, I'll let you go through these yourself, but obviously you have relationships which are commutative and multiplicative and so forth. One of the things we're going to do in this course is we're going to use changes of variables. Sometimes you're going to be looking at something and it's just not going to work. There's a great change of variable problem for fractured wells, because we need to recast the formulation, and you'll see that later on. But be aware that we will use change of variables, we will use these different rules. We'll split an integral in two and reverse the limits. We'll do all sorts of things that you see on this page. So this is pretty basic stuff, but if you're uncomfortable with it, go back to the text, the Sham's outline, and make sure you familiarize yourself with it. Integration by parts, as promised. Avery. Use the product rule. And we then multiply through by dx. And that gives us this form. And then we look at that, we stare at it, and we say, oh, we can integrate that in definite integration. So that gives us the UV product, and then we have the integral of U with respect to dV, and the integral of V with respect to du, and we just complete the integration. And we usually solve for the form of the integral of U, dV, UV minus V du. What are the rules? Well, dV should be integrable. What should be integrable mean, French guys? It means it should be easily integrated. If it's not, then we got a problem. And then the integral of v du should be easier, or should not be more complex. How do you feel about that? So Avery, this is what you were talking about earlier, in a way.
That's what I did.
So if you choose this incorrectly, what's going to happen? you're just going to get into a dead-end street. You're going to say, I can't do any more with this. So integration by parts is something that either works or it doesn't. It provides a solution, perhaps, to certain kinds of problems. You'll know when it arises. Questions or comments about integration by parts? Again, we're sort of talking about swimming rather than swimming, but I think you get the message. All right, next is the discussion of increasing and decreasing functions, and there's a reason I wanted to bring it up. Why? For an increasing function, using an approximate integration, you're always going to underestimate the integral. For a decreasing function, don't know what's going to happen there, but you're always going to overestimate the integral in that fashion. Okay? Just be aware that you'll need to recognize what's going to happen with this. Is that always going to be true? Yeah. Okay, now this is a derivation of the trapezoidal rule using a graphical approach. And as someone pointed out earlier, we have the rectangle. And the rectangles are given here. And then we have the resulting triangle, and they're given here. And for an increasing function, again, we're still underestimating the area under the curve, or the integral. We simply do the algebra, and it turns out that whenever we look at this, the f of x of I plus f of x of I plus 1, that times a half is equal to that portion, and then it's the differential over which it's applied. So if you can imagine, what you're really looking at is a rectangle that's roughly here, and this would be f of x I plus f of x of I plus 1, that divided by 2. So essentially you're just creating an arbitrary rectangle at that point over that width. Is everybody comfortable with the trapezoidal rule? I think so. I mean, everybody in here should have talked about the trapezoidal rule at some point. Questions or concerns? Paul, how would you derive Simpson's rule? Avery said it earlier, you'll have to use the Taylor series. Okay. Simpson's rule is derived for you in the Hornback text, along with some of the other traditional integration formulas. You've come up at a time when everything you ever wanted to know is in Mathematica or MATLAB, adaptive methods, direct methods, and so on. But if you want to get a feel for how to derive these things and understand what their errors are, then go back to the fundamental text like Hornback. There are going to be a massive number of books written on things like quadrature and other elements. Try to use the standard references or you'll lose your mind. I'd probably start with Abramowitz and Stegan. Okay, we have a discussion about some, I put this in just so everyone remembers what the definitions are. French guys, do you remember how to derive this? I don't remember how to derive it either.
If you try to derive it, then you integrate the limit and the integrate and the derivative, and then you evaluate it in zero. Maybe you find the
something like that, yeah. It's obviously not a practical formula, because you can't let n go to infinity. Where did this come from, class? You remember from the last lecture?
The function.
How did we derive this? This is from Taylor series. Okay. And then we have the operations, and of course the derivative of an exponential is an exponential, and the integral of an exponential is an exponential. And then we have some rules for exponentiation, and I'll just leave these to you. Okay. Everyone remembers these? No big problem with this? Everybody seems to be happy with that. Also, there's some special values for the exponential. exp of 0 is, of course, 1. exp of 1 is 2.718, blah, blah, blah. The exponential of infinity is infinity. The exponential of minus infinity is 0. So, how does a computer calculate exp? Anybody? Should we ask how do calculators calculate?
In general, it doesn't say add, subtract, multiply, divide, and has logic functions, but
Well, let's see what this guy says. Oh, this looks like gibberish. Is it? They're using some sort of a series, and then product forms, and then they show how to do this. What year is this? And this is old school. You should always put your year on things. It must be pretty recent because they've got a URL. Okay. Anybody else? So let's look at Fortran. Somewhere there should be a subroutine. Any ideas? I don't think they're going to give us anything meaningful. Where's that GNU Fortran thingy? You'd think they'd tell us. What are they afraid of? Why don't they tell us?
we always think that it's perfect.
So there's a Taylor series. How about just Fortran subroutine? And let's make it good for us. You guys see any code? What about this Pierre Moreau guy? He didn't tell us anything. I want to see something crazy.
I have some idea. When we take a ratio of one time and the next time, it can be written as a formula.
Right, but I want to see the formula.
It is very easy, like x divided by n, something like that.
No, but I want to see a subroutine. They should have it in here. Fortran.
I mean, it's literally just a Taylor series, but they have a very small column. But how do you run it compared to what it should be? Never mind.
See what they tell us here. This guy, he's got all this stuff, but he doesn't tell us anything. There's Bessel F90. There we go. How do you like that? Look at all those coefficients. That doesn't give you the heebie-jeebies? Where's something interesting? I don't want to see a table. I want to see the real deal. Here's the gamma function in Fortran. There's nothing there. I was robbed. Give it up. I want to see it. What was it, the gamma function? Is it M gamma? Yeah. Where's the zip file thingy? I never do this right.
It's one of those folders you have opened up. You click next
You
to
think?
it.
Doesn't look like... Oh, there it is. Thank you. You're a good boy. Was it MC gamma? No, there it is. Uh-oh. Something bad's about to happen.
Virus.
This is bad. What should I say here? Visual F? Just generalized. There. It may take a few minutes. I just want to open the stupid thing. Doesn't it give you open with anymore? Alright. Well, we'll forget about that for now. I got it, okay? I broke it. I'll fix you. Okay, anybody got any ideas what this is going to look like?
When you evaluate it close to zero, maybe they don't give you the answer.
Okay, I'm going to try it this way. Somebody stop me. I wanted to open it Can it open it with Notepad?
You might have to pull it out from the zip. It's still in a zip.
Yeah, I know you're right. Uh-oh. Something's happening. There it is. Okay, so it's got some coefficients and stuff. Man, this guy writes really compact code. Would Dr. Morides like this?
No, in the function you can calculate using intrinsic function.
No, no intrinsic. You gotta make your own function. That's what I was saying.
Yeah, we can calculate it by ratio. And
But not every function can be represented by intrinsic function. Yeah?
not every function.
I mean, like, if I wanted... Where's his Bessel function? Do you guys see Bessels? I'm looking for the K's. Alright, we'll just say this one, my JY. My JY what? My JY in A. Okay, so here's how he calculates Bessel functions. And he's got to have, oh, here we go. Where did these come from? Do you know? Sorry?
No, Ramanujan.
Where did this come from? You should always tell where you get stuff from, right? Anybody want to guess? Miss Kim? Yeah.
I'm Lee.
Miss Lee, sorry. We call you KJ.
Yeah, right. Actually, I can hardly see.
You can hardly see, so you're saying you want it bigger? How do you make it bigger? I've never opened this before. Where's font size? Thank you. Is that big enough? Anybody? No idea. Paul?
It looks like one of them.
Oh, man. You have to turn this thing to never, or you don't get the slider bars. Don't forget. Alright, so we need Bessel functions. Bessel function. While we're still young, right? Bessel functions, approximations. Anybody see Bessel function? Asymptotic expansion, formulas.
Interpolation. Bessel's interpolation.
No, I'm looking for polynomial approximation. 369, right? I'm getting warmer. Okay. So, does this look familiar? This is on x to the 4th. These are on x to the 3. I think there's a modification of this. See, they mapped it to plus or minus 3 here. And I think these guys mapped it to plus or minus 4. I think it's more or less the same thing. So somehow you have to get an equation for this. Not sure I understand where the 3 and the 4 come from, but okay. By the way, where did these equations come from?
Which
These.
polynomial is not constant here.
They're taken from E. Allen, Analytical Approximations, Math Tables, AIDS, Computation, 1954, Polynomial Approximations and Modified Bessel Functions, blah, blah, blah. So it came from, somebody figured it out. Okay. All right, well, we'll get out of here for now. I know you're tired of looking at this. Sorry. What was the purpose of that exercise? To illustrate that you take for granted when you push a button on your calculator, you get a number, or the intrinsic function. Here's the rules for logarithms, and if you ever have me for a well testing class, I ask these fundamental questions, and if you ever skip a step, I will punish you. This is the definition of the natural log. It is the integral from 1 to x of 1 over x dx. It's not just you write it out. That's the definition. Okay, the other thing we need to remember is down here that the logarithm to whatever base you're using of x over y is not the logarithm of x over y. It's the logarithm of x minus the logarithm of y. That's probably, I'm making a big deal out of it because that's the one I always forget. So remember that. And then you have definitions of derivatives, and you have some special numbers given over there. Any comments or concerns about logarithms? What do you think the equation looks like for calculating the logarithm in a computer? Does it look like this? What does it look like? How do you remember where the 1 goes? Because the logarithm, oops. Oh, that's not working. That was pretty cool, though. It worked for a minute. What's the integral of 1 to x if x is less than 1? It's a negative number, so that'll help you memorize that. I'm not going to bore you with trying to look up what the logarithm is. We'll move on. Okay. Taylor series. This is the part I messed up on Friday night. This is the definition of a Taylor series. This is taken straight out of your Hornbeck book, which you have access to. and you're looking at f of x is expanded around some point A, and as someone mentioned earlier today, I think it was Ralph, that we just need to be relatively close to A. So in this case, we're looking at x minus A times the derivative with respect to A, or at A, x minus A squared over 2 factorial, and then second derivative and so on, and we carry it all the way out. Now, if we have a function that is infinitely differentiable and we can represent it by a polynomial, this is what will happen with a Taylor series. In a few minutes, I'll show you an example of how some people use the Taylor series and some people didn't. Generally speaking, Taylor series are not going to be particularly effective for what we want to do. But you may be able to use the Taylor series to represent something. The author did a really good job here illustrating how the Taylor series represents an approximation. The first approximation that he's talking about, we know the value at A and we want to extrapolate to B, so that's the constant. The next one is a linear, and then the next one is a quadratic, and we just keep going until we finally have an expression that is sufficiently accurate to estimate at B. And of course, some of this has to do with the location of where we're at. But as a graphical explanation of what we're doing, this is a representation of what expanding the function around A and how we have to approximate that, and it takes higher order derivatives to get us there. So I thought that was pretty clever and thought it might help explain this if you wanted to know more about it. Okay. So this is where we started last time. We were talking about Taylor series, and I wrote in how the Taylor series is expanded and then how we take its derivative. And the important thing to realize is that every derivative has, okay, so f of x is equal to a0, that's the starting point. F prime of x is equal to a1, that's the starting point. F double prime of x is equal to 2a2, that's its starting point. F triple prime of x is equal to 3 times 2 times a3, that's its starting point. So what this tells you is that whenever we look at x equals to c, what happens? Well, this goes away, this goes away, this goes away, this goes away, and so on. So when we evaluate these at x equals c, then we get these coefficients. And of course, we can rearrange, and a0 is the value at f of c, a1 is its derivative, a2 is 1 over 2 factorial times the second derivative, a3 is 1 over 3 factorial times the third derivative. So this is where you were talking about earlier, Ralph, that as long as you have an infinitely differentiable function, you can represent this. So you'll just have to keep carrying out terms. Okay? And finally, we have this as our final expression. So this is how we'll represent our expansion. In a moment, we need to recognize what our terms are. So we need to know, if we're going to perform this expansion, what f of c is, f prime of c, f double prime of c, and f triple prime of c. We need to know what those are. So that's the key to this. The function must be analytic, must be completely differentiable. Okay, so we did this last time. This is the exponential, and of course we mapped it, and we've already seen the exponential, and I'll write it out so that everybody at home can see it. But the final result is this. So that's our final result, and it was obtained by estimating the function and all of its derivatives at 0. So this is EXP expanded around 0. How accurate is this going to be? What's your intuition tell you?
It depends on it.
Only near 0, right? Now, one of the things that you'll learn in your reservoir simulation course from Dr. Wattenbarger is near 0 you're going to use this, which is obviously okay. You will have an exponential function that doesn't vary much. Okay, this is our friend Hastings et al. And what you're looking at from Mr. Hastings, and unfortunately you can't read this, so I will expand upon it. But this is not EX, this is e to the minus x, like that. And they've mapped it over the entire interval from 0 to infinity. Obviously it dies off. And this is the min-max polynomial error. Over an interval that they've mapped at. So how good is that? Is it good enough?
We don't see the figure.
Sorry?
We don't see the figure.
Okay, it's very, very small. It's 10 to the minus 7. Okay? This was 1955. They only had single precision calculations. What would you expect now? How small would you expect this now?
Depends on what
This is approximately 1 times 10 to the minus 7. What would you expect now? You'd expect machine precision, which on a PC is what, 1 times 10 to the minus 333 or something ridiculous like that. But most of the time you start seeing overflow on EXP at something like 1 times 10 to the minus 22, so you may have to safeguard it. I think that may have been where you were going, Ms. Lee, about using intrinsic functions, because the intrinsic function in Fortran, for example, begins to fail for arguments, at least back when I was doing it, arguments say greater than 1,000, it's going to start to fail. Okay. This is a very interesting functional form. What kind of functional form is this? What's it called? Does anyone know? Paul? This is called a rational polynomial. Why is a rational polynomial good? Jorge? It's 1 over a polynomial. Generally speaking, that's not a very good idea, is it? Why? Because it has zeros. And what happens when you take 1 over 0? It's going to explode. So we hopefully have mapped it in such a way where the zeros lie outside of our interest. Otherwise, we're going to have a serious problem with this equation. Okay. So this was the 1955 version of Excel, if you want to think about it that way. You would have had to taken this equation and programmed it, and it would have given you a calculation. This is, again, a min-max polynomial. There was some sort of an optimization scheme they used to estimate this. Everybody okay with that? What did the Russians do? Well, for those of you looking online, there's no mystery. The Russians used what? What does this look like? Sorry? It looks like a Taylor series. Do you remember what the Taylor series for EXP was? It's 1 plus what? X plus x squared over 2 factorial plus x cubed over 3 factorial plus x4 over 4 factorial plus x5 over 5 factorial plus x6 over 6 factorial plus ... Why did I write all these out? Because this is 1, this is 1, this is a half, this is 1 over 6, what's next? Is it exactly 1 over 6? Is it exactly a half? Why do they have round off? I don't know. I'm not sure how they did this. Does everybody understand? This is the Taylor series. This is their expansion. Let's do it again. So what's the first term? This should be 1. What should this be? 1. What should this be? 1/2. What should this be? 1 over 6. What should this be? What should this be? What should this be? And so on. Did I get that right? I mean, I know they were doing a little bit different, but they basically used the Taylor series. I think they may have mapped the outer edges of it. I'm not sure what they did here. If you really want an interesting read, maybe even over here, I'm not sure what they did. They wrote on there that on Soviet computers, this equation works. On Soviet computers. I didn't realize computers had a nationality or a political affiliation. Why torture you with all this? Why do this? Anybody? Schmuck?
I was thinking, why do we need in the industry to calculate
You don't.
so many decimal points?
Oh, well that I can't answer. But the reason we're going through all of this is at the end of the course, when we're developing the reservoir engineering solutions, let's say you want to use an approximation. Your brain is going to say, oh yeah, I can use a Taylor series, or I can use some other expansion. Do we do that, Paul? Yeah, we do. Okay. And we have to understand what those expansions mean, and what, when we truncate terms, why we did it. Now you were asking, why do we need so many decimal points? You've been in the field too long. Okay. Any thoughts or comments? So what do we want to talk about tomorrow?
Approximation of functions?
Sure, why not? And then our last slide is the sine series. which we talked about the other night, and we saw it didn't work very well. But as it turns out, all we really need to do is map 1 quarter of the period, and we should have that taken care of. Okay, so for tomorrow night, we'll talk about functional approximations. And again, we'll talk a little bit about Taylor series and Chebyshev polynomials and so forth. And again, it might be useful to use a Taylor series expansion, which is what we have here for Earth. We use the Taylor series expansion to derive that. We'll talk about this tomorrow night. What's a Chebyshev economization? Before we go into it, what's a Chebyshev economization? John, do you remember? You know, some people devoted their lives to things, right? What Chebyshev did is he developed a series of polynomials that would allow you to conceivably reduce the order of a polynomial and still obtain accurate estimates. Now, you never get something for nothing in mathematics. So what happens with Chebyshev polynomials is you do have a reduction of order, maybe a simpler polynomial, but how does a simpler polynomial represent the same thing? Okay, well, we'll talk about that tomorrow night. I'll leave you with, some drama in your life. Okay. We are not going to use a whole lot of this in this course, but there may be a need for some sort of an expansion or some sort of a calculation, and we'll talk about that. Questions, comments, concerns? Okay. All righty. Tomorrow night. Paul, don't forget to turn everything off, or they'll get really mad at us. Somebody turn the lights on before we start playing mood music. Okay, questions or thoughts before we leave?
You asked the question, why did you use it? You did that thing.
Well, at the end of the course, we're going to make some very heavy derivations, and then we're going to want to approximate them. So we might use a 2-term approximation or a 3-term approximation or even a 1-term approximation for a given function. And we have to know where that function came from and why we're doing it. That's what this is all about. Are we going to make Taylor series expansions for a living? No.
So what kind of expansion are we doing?
No, I didn't mean it like that. I mean, that's not the purpose of the class. The purpose of the class is whenever we have this complicated Bessel function behavior, we might take and use some other alternative form.
Do we find them in an endbook or to do it?
We'll do both. It's all written out. This is a very easy course to work with because it will give you everything. So you like your toy there, huh?
We have to.
You could cut the end off and put another plug on it. So I worked on this program in Mozambique, and they gave the students all computers, right? But they ordered the computers out of South Africa. Have you ever seen a South African plug? It looks like this. It's got 3 prongs, but they're about as big as your fingers. And so they gave everyone a converter. And I noticed that the Mozambicans, about 5 or 6 of them, had already cut off the South African plug and put the standard European plug on theirs. So, yeah. What about Mexico? Oh yeah, you have the same one as us. Yeah. So why does North America, Mexico, United States, Canada, Venezuela, Saudi Arabia, why do we all use 110 voltage? and everybody else uses 220,
Why do you have feet and inches and everybody else has meters?
because we were right. I remember when I was young, we tried to change to the metric system. It didn't work out so well. To me, I don't know why we don't just say, let's do it, but, you know, that's life. If you're gonna work in the oil industry, better get used to feet and inches and things like that. Yeah. I was in a class a while back that some drilling guy was teaching, and someone kept saying, we have to convert everything in drilling to the metric system. Take a deep breath. How do you measure pipe in Argentina? And what kind of, is it 8-round drill pipe? It's standard 8-round connections, right? And inches. What about in Mexico? What about in Korea, in, you know, wherever?
Even in France.
Why? Because all the manufacturing was set up for that. And so this guy's screaming, you know, you have to change to the metric system. You know how much money that would cost to switch? Anyway, the oil industry will be dead before that happens. So you can worry about it later. All right, well, everybody have a good night, and we'll see you tomorrow. Take care, everybody.
I couldn't get out of my lab. They had so many questions. We were doing, first class. Where? I like them.
We know wells are close, but we don't know whether we have the right to land them or not, so we're going to check it out like French people.
I have one, at least, so I can buy it. I can buy it. So. Más o menos. ¿De qué tal? ¿De cómo te crees?